Okay, we're going to move on to the last topic of the year, first law of thermodynamics. Okay, this is the last topic that will prevent you from going on your December holidays. Alright, but we decided to cover this so that it's linked up nicely with your previous chapter, the one on your internal energy. Okay, and these two topics are not too difficult to manage. Alright, so anyway, you see on my screen now, you will see that there's this glass beakers at the back with colorful floating bulbs inside them, right? And you'll be wondering what exactly it is, right? So let's just quickly show you what these are. Okay, this is basically called a Galileo thermometer. Alright, it's basically a thermometer. You can see that there are different bulbs with different colors, liquids inside. There are different liquids as well. They have masses attached to them. And what happens is that you will put them into this glass cylinder sealed up, and when the temperature of the air changes, it affects the temperature of the water here as well. So different they will float at different levels. Okay, so the temperature is given by the lowest floating one. So let's say that 1 2 3 4 of them have sunken down to the bottom. This one is the lowest floating one. Then this is the current temperature. um not much links to this chapter per se, but then I think it's quite interesting. It's still linked to your thermal as well. Okay, so for this chapter, you'll be doing three main areas. We will probably take about 3 lectures to cover this whole thing. There's specific heat cap and specific latent heat, which I learned probably at Sec 3 and Sec 4, and then internal energy and first law of thermodynamics. Alright, this chapter is probably, I feel, is a bit easier than the previous one because it's quite logical. To a large extent, it's quite mathematical as well. The calculations are simple. You will see that it's quite simple to do. It's not very difficult math. You just need to understand some concepts. Anyway, that's what we say for all chapters, right? So you can try and see how it works. All right. Okay, so this is a typical four-stroke engine used in cars. Okay, right now what's happening is that, okay, your green color, here is a fuel that's coming in, is mixed with air coming in from outside. Okay, and what happens is that this is your piston. The piston is moving up and down. Okay, it compresses the gas, it compresses the fuel and comes in, and then the spark plug will light up over here. Okay, once it lights up, it causes the gas to expand, and then basically it will push the cylinder down. So this process will continue itself. These are known as the valves. The valves basically let the air and the gas and the fuel come in, and then also exhaust out. Okay, so why is this picture important here? Because what we're trying to show is that basically gases, when they expand or contract, right, they can be made to do work as well. Okay, so we can also do work on gases just by compressing them. We can add energy to gases just by compressing them. We can take away energy from gases by allowing them to expand. Okay, so this is a bit different from what you've learned so far, where the only way to cause a gas to gain energy is to heat it up. The only way to cause a gas to lose energy is to cool it down. Alright. Okay, so let's just recap a very basic concept. For two bodies in thermal contact, total heat gained by one body is equal to the total heat lost by the other body. Okay, this is assuming there's no heat loss to the surroundings. That means, let's say I have object A, object B. A is losing heat to B. Whatever heat is lost by A is gained by B. Okay, note that we don't need to use thermal energy or heat energy. We just straight away say heat. Okay, is known as is fine. You can just go as heat. All right. Okay, so let's look at the first definition we have. We have heat capacity. Capacity C of a body is defined as the amount of heat that must be supplied to it to cause a unit rise in temperature without a change in state. Alright, so there's some terms we need to take note here. Amount of heat that must be supplied. Okay, so how much energy must I give it? Okay, to cause it to have a unit rise, to have a 1 degree Celsius increase in temperature, or 1 Kelvin increase in temperature without a change in state. So if it's solid, it will stay solid. Gaseous will stay gaseous. Liquid, it will stay liquid. That means it's not near the boiling or melting point. Okay, so equation is just very simple. C equals to heat supplied divided by delta theta, change in temperature. Alright, of course, if you are talking about heat loss, this will also work as well. So how much heat to take away to cause a 1 degree change or 1 degree drop in your temperature? Okay, of course, the units is just this Q is Joule, and then temperature is Kelvin. Alright, you do remember that for Kelvin and degree Celsius, right, the increment in 1 Kelvin is the same as an increment in 1 degree Celsius. Okay, so you can just sub in for this equation if you have to use it, just sub in terms of degree Celsius. There's no real need to convert it to Kelvins. Okay, so this one seems quite useful, but then we realize that actually if we go and look at these two substances, 32 kg of gold and 1 kg of water, right, they actually have the same heat capacity. Okay, what I mean by that, if I supply a certain amount of energy to gold, it will increase in temperature by a certain temperature. But if I take the same amount of energy I give it to 1 kg of water, right, it will also increase by the same temperature as well. So having heat capacity alone, right, is not sufficient because it does not distinguish between two different types of material. So if I have, let's say I give you another picture here, let's say I give you another sample of 1 kg of gold, right, that 1 kg of gold, you expect it to gain more temperature if you have the same supply in heat. So we need to go one more step and start to say, okay, can we just do this division by delta theta? Should I also bring in mass? And when you bring in mass, what you do is that you have specific heat capacity. Okay, so specific heat cap, usually we use a small c, is the same as heat cap, just that there's a unit mass of the substance to undergo a unit rise in temperature. So that means how much heat must I supply to cause 1 kg of the substance to undergo a unit rise, to undergo a 1 degree Celsius rise in temperature without a change in state. So now this is Q over m delta theta. Okay, we're taking the mass. Okay, so now this one, note this difference. This is heat capacity of a body. Okay, so this body here will have to take into account the mass as well. Okay, but for substance, we basically divide by mass, right? So this is basically, if you have, say, heat capacity of gold, right, this will apply for all samples of gold, regardless of the mass. Okay, so we have different materials. For some common materials, you have the different heat capacities. This is joules per kg per Kelvin as well. And you can see that basically metals have very low heat capacities, which is why metals will heat up very, very fast compared to, let's say, something like water, which is about 4,000 joules per kg per Kelvin. All right. So if you look at your typical containers at home, you have aluminum 887 and then water 487. Okay. All right. Let's move on. Okay, let's look at the first question here, example 1. How much energy is required to heat up a piece of copper or mass 275 grams from 14 degrees Celsius to 100 degrees Celsius? Specific capacity of copper is 380 joules per kg per Kelvin. Okay, so let's look at this. Okay, so this one is just a direct substitution. Okay, Q equals to MC delta theta. I basically just rearranged the equation from just now. Because this is given in terms of grams, I need to convert the grams to kg, so divide by 1000. Multiply by heat capacity, specific heat cap of copper, 380 joules per kg per Kelvin, and multiply by the change in temperature. So I get 8990 joules. Okay, this is 3SF to me, you can round it off to you can round it to 9000, that's why it works. Alright, so just a very basic example to get you used to using the equation. Alright, next I have a kettle that has a power of 5 kilowatts that's used to heat up a piece of 500 grams copper from 10 degrees Celsius to 90 degrees Celsius. Given that specific heat cap of copper is 380, calculate the time taken for the heating process. State any assumption made. Okay, so just now I reminded you that there's no heat loss, okay, but in reality, right, there's heat loss to surroundings as well. But for this case, the assumption that we're making is that there's no heat loss from the system of the heater and copper to the surroundings, right? Okay, so for this, when we do calculation again, this is PT, because now we are talking about power times time. We are trying to find the time here, okay, because this is Q equals to MC delta theta, and Q is the energy supply, which is basically power times time. Okay, again we make the same substitution. P is 5000 watts, and then mass is 0.5 kg. heat cap is 380 and change in temperature is 80 degrees Celsius. Okay, and once you do the math, you realize that T is about 3.04 seconds. And realize it's quite fast because the heater is quite powerful and you are dealing with copper as well. Okay, so I think this is again very straightforward because there's no heat loss. Okay, later we'll see a question that involves heat loss, so that one's a bit trickier to calculate. Alright, let's go on. Okay, next we have a restaurant that serves coffee in small copper mugs. A waiter fills a cup of mass 100 grams initially at 20 degrees Celsius with 200 grams of coffee initially at 70 degrees Celsius. What's the final temperature after the coffee and the cup have attained thermal equilibrium, assuming there's no heat loss to the surroundings? And you're given the heat capacity of copper, the specific heat cap of copper, and also coffee. Okay, in this case here, right, because coffee is hotter at 70 degrees Celsius and then the cup is cooler, so we expect the coffee to lose heat and then the cup to gain heat. Okay, so how to do this calculation? Yeah, okay, so first let's define theta to be the final common temperature. Okay, the coffee will cool down, the cup will heat up, so eventually they will settle at a temperature. Once they hit thermal equilibrium at the temperature, there's no more heat transfer. Okay, so heat loss by coffee equals to heat gain by cup. All right, so let's do this calculation. Okay, so I do for coffee first. 0.2 times 4002 joules per Kelvin per kg times 70 minus theta, from 70 degrees down to theta. And then this is 0.100 times 380 times theta minus 20 degrees Celsius. Okay, note that heat loss is a positive magnitude. Okay, I know here, right, we know by I read this heat loss by coffee, it should be, if you think about it, it should be from theta minus 70. Okay, the final temperature is theta and 70 is the initial temperature. Okay, but if you do that, right, you will definitely get a negative value on this side here. Okay, but by using the word loss, we have already said that we know that this is a negative value. We are just going to take the positive of it. So basically, when I say heat loss equals to heat gain, I'm saying the magnitude of heat change by the coffee, heat transfer by the coffee is equal to the magnitude of the heat transfer by the cup. Okay, that's what I'm doing. Okay, so once I do this and I do some algebra, I'll get theta equals to 67.8 degrees Celsius. All right. Yep. So you realize it's much closer to the initial temperature of the coffee. Okay, mostly because of two factors. One is easier for the copper to gain temperature just by absorbing a fixed amount of energy because of the lower heat capacity. And second reason is because there's actually more coffee than your cup mass. Okay, so that's these two factors will swing it towards a final temperature that's closer to your initial temperature of the coffee. Okay, so let's move on. So that was just a very quick recap of your specific heat capacity. Now we move on to latent heat of fusion. Okay, latent heat of fusion is when we are talking about phase change from solid to liquid. Okay, so let's say for example you talk about ice. If you have ice that's going from negative 10 degrees, you heat up the ice, it will go from negative 10 to 0 as ice. But to become water, right, it has to do melting first. It has to be melted, that means more energy has to be supplied without a change in temperature. Okay, so specific latent heat of fusion, LF, of a body is defined as the amount of heat that must be supplied to cause a unit mass of the body to undergo a phase change from solid to liquid without a change in temperature. Okay, so basically what I do is that if I go and find out how much heat is needed to melt X kg of that solid, I just divide this Q over the mass of the object. So this is the latent heat of fusion. Alright. Then of course you have specific latent heat of vaporization. Okay, so now we are dealing with going from liquid to vapor, a unit mass of it. Okay, so same idea. LV equals to Q over M. Units is joule per kg. Alright. And once we have that, okay, we can look at some of the values. Okay, over here we have I put in the LV and LF of some common substances, and you realize that typically, right, the specific latent heat of vaporization is much higher than the specific latent heat of fusion. All right. So you can see that for water, right, there's a 6 times difference, and for nitrogen, it's almost 8 times difference, and for, let's say, aluminium, is a 355 times difference. Okay, so it's a very, very large difference in values. Okay, but you might ask yourself, it's just the same change in state, right? How come they are so different in terms of value? Yeah, one is from solid to liquid, the other one from liquid to water. Why is there such a big change in the values? Okay, because what happens is that when you go from solid to liquid, your volume doesn't change by a lot. Okay, and what happens is that when you go from liquid to gas, it changes by much more. So in order for from solid to liquid over here, you can see that basically the volume is a change. So if the volume is the same, right? More or less the same, right? The object, the body has not done any work against the atmosphere yet. But for gas, if you want to go from liquid to gas, you realize that it has to go to occupy a larger space. Remember, when it occupies a larger space, it has to push away the existing atmosphere that's there. It has to do work against the atmosphere. Okay, so therefore you need to do more work. Therefore, you need more energy to convert from liquid to gas than from solid to liquid. Another reason is because, remember, your spacing will affect your potential energy. So if you go to a larger spacing, okay, you have a larger change in spacing, you need to gain more energy. You need to gain more potential energy. Okay, so if you look at solid to liquid, right, the change in spacing is quite minimal, but to go from liquid to gas, the change in spacing is actually quite significant. So usually, okay, I think most of the time, LV is much larger than LF. Okay, okay, so we'll look at some questions for this section here. Okay, look at this one. Calculate the amount of heat required to completely boil off 1.5 kg of water, which is initially at 25 degrees Celsius. And we gave you the vaporization, the LV of water and the specific capacity of water. Okay, I remember the boiling point of water is at 100 degrees Celsius. So even before you can start boiling, you have to bring the water's temperature up to 100 degrees Celsius first. So you need two types of energy. You need energy to do two things rather. First, to raise the temperature of the water from 25 to 100, and then you need energy to boil off the water as well. So we do MC delta theta plus MLV. Okay, 1.5 kg times the specific heat of water 4002 times the change in temperature, which is 100 minus 25, and then plus 1.5 times specific latent heat of vaporization of water. So you get 3.86 times 10 power 6 joules. Okay, so straightforward calculation. Okay, let's look at example 5 now. Okay, example 5, we have 1.5 kg of water operated by a 2000 watt heating element. Okay, so in most kettles there's a thermostat. Okay, so for thermostats, what they do inside the kettle is that once the water temperature hits 100 degrees Celsius, it's assumed to be boiling, and then after a while the thermostat will switch off the kettle. So this will prevent your water from being completely boiled off. So if the thermostat fails to operate, right, the water will keep on boiling until it goes off. Okay, so if 1.5 kg of water at 100 degrees Celsius powered by 2000 watt heating element. So heat supplied by the kettle is equal to the heat gained by the water as well. So PT equals to MLV. Okay, and we are supposed to find time. So this is 1.5 kg times 2260 kilojoules, because there's 10 power 3 at the back, divided by the power of the kettle. Okay, so you get 1695, which will translate to 1700 seconds. Okay, now let's do a slightly more complex question. I have 0.1 kg of a liquid that's vaporized completely in 15 minutes after an immersion heater set to a power of 240 watts. Bring the liquid from its initial temperature to its boiling point. Okay, then after that, I repeat the experiment with the power increased to 420 watts, and the same period of time, 0.15 kg of the power of the liquid is vaporized. Okay, so this time here is after the water is at the boiling point, and then you start to let it vaporize off. It does not include the time for you to bring the liquid up to that boiling point temperature. Okay, But what's interesting here is that you are given two sets of experiments. So basically there's case 1 and there's case 2. Okay, if you choose to use case 1 alone to calculate the specific heat of vaporization, and then you compare to case 2, you realize that the answers are not the same. Okay, because in this case here, there's actually heat loss to the surroundings. So we need to use the two cases to go and establish what is the heat loss, okay, and which is for the next part. Then we can, after you can use it to solve for the specific latent heat of vaporization. Okay, so we're going to make one big assumption here. Both cases have same rate of heat loss. Okay, basically what's happening here is that, okay, how do I come up with this assumption? The liquid container is the same, so it's exposed to the same atmosphere. Okay, the total surface area is the same. The boiling point of the liquid is the same for both cases, so the temperature difference with the surroundings is the same. So it will tend to evaporate at the heat loss will happen at the same rate. So this heat loss, right, remember, is just heat from your heater that is supplied to supposedly to the liquid. But in this case, right, it's being wasted. It's just loss to the surroundings. This happens when you do not insulate your container. Okay, so let's make use of these two calculations, these two cases first. Let's look at case 1. Case 1, I will write it this way. So this 240 watts is used to do two things. Okay, so first it will boil off 0.10 kg of a liquid. Okay, multiply by the LV, and then this is the heat. This is Q. This term here is Q. Okay, divided by the time of 15 times 60 seconds. Okay, then plus H over T at the back. Okay, so H over T is the rate of heat loss. And I rearrange the equation, I get this H over T equals to 240 minus 0.10 LV divided by blah, 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 15 over 60. You can check the math later. Okay, for case 2, we do the same thing, but now my heater is 420. The timing now is 12.5 minutes, 0.15 kg is evaporated. Okay, again, plus the same H over T at the back. Okay, rearrange this equation, you get a similar form to this one. And once you have this two, it's quite easy to do. Let me just put it over on this page, has a bit more space. Okay, so what I do is just equate equation 1, equation 2 to each other. You just equate H over T, because both of them are H over T. So you write out this equation here. Then once you have this, then you apply some algebraic magic. You can do the math yourself. I'm not going to do it here. Okay, try to find LV. And once I've done that, LV is 2.03 times 10 power 6 joules per kg. Okay, so this, by equating them together, I have taken into account heat loss to surroundings and then basically remove that effect. Okay, next, determine the percentage of heat that was lost to surroundings in the first attempt. Okay, so this one over here, we have to use the first attempt, so equation 1. Okay, what we have done just now is that we have found out LV, right? We can sub LV into this equation here, and then we can find H over T. Okay, so we sub this in, sub over here, you get H over T to be 14.45 watts. Okay, and once that has happened, okay, you can work out percentage heat loss. 14.45 divided by 240, which was the heat supplied by the immersion heater, and then multiply 100%, I get 6%. Okay, I think that's the last for this first lecture. It's quite a short lecture, it's about 25 minutes. So that leaves you plenty of time to complete your exit pass 1. Okay, so you can scan the QR code now, or you can just type in the link. Okay, remember we are tracking the responses, especially if you fall into the case of advanced or weak advanced. It's really important for you to stay on track before you get to JC2 proper. Okay, so I'll leave this here for a while and then you can do this. Okay, or if not, just pause the video. Right, at the start of the next lecture, we will go through the exit pass questions first. So before you watch the next lecture, please complete your exit pass 1. Alright, otherwise, that's all. Thank you. Have a good day.